Greetings, everyone. Today we're going to explore using logs to solve equations. Let's take a look at a real-life application of when would I actually have an equation that involved a log. Tornadoes can use this formula to find the speed near the center of the tornado in relation to the distance the tornado traveled. So, for example, in Moore, Oklahoma in 2013, we had a tornado that traveled approximately 17 miles. It was a very devastating storm due to the speed. So let's take a look at the estimated speed. If I was to solve, I would start off by replacing the d value with the total distance traveled. If I have 93 log base 10 of 17 plus 65, I can use my calculator to solve that value. Now notice that it has a base of 10. When we have a base of 10, based on the previous lesson, that's called our common log. So you don't need to do any change of base formula. You can just plug this straight into the calculator just as you see it. So in my calculator, what I'm going to type in is 93 log 17. Now your calculator will start a parenthesis, so you should end it, plus the 65. If your calculator does not create a parenthesis for you, then you'll want to make sure to include parentheses because you're not adding 17 and 65. You should end up with an estimated speed of approximately 179 miles per hour. So let's further explore what if my variable or my unknown is next to the log or part of the log. So based on converting, we know I could convert this to exponential form. That would give me a 2 to the 6th equals x. And this, I can use my chart, I can use my calculator, but I can arrive at that solution of x equals 64. Now, if I wanted to check my answer, I could use change of base and say log of 64 divided by log of 2. And if I type that in, I better end up with 6. Otherwise, something is up. Let's take a look at some examples. In this particular example, the equation is balanced. And what I mean by that is there is a log on each side. So similar to change of base, let me quickly review that the method of common bases. If I had 2 to the x equals 8 to the 2x plus 1, we worked on this earlier. We said, okay, I need the same base. So this would be 2 to the 3rd. Then we said, okay, I have the same base. So we actually set the exponents equal to each other. It's almost like we didn't need that base anymore. The equation was balanced in that each side had a base of 2. And then we went and solved from there. We don't need to continue that. But logs work similarly. If I have an equation balanced with the same log on each side, it's almost like I can drop that log. So in this case, I would be left with my two expressions equal to each other and therefore an algebra 1 equation. So I'm going to quickly subtract that 1x over, I'm going to add that 7 over, and I'm going to divide by 3. So to check my work and see if I'm good to go, if I was to plug in 4 into my expressions, 4 times 4 is 16, 16 minus 7 is 9, equals, if you look at the other side, log base 5 of 4 plus 5 is 9. So without even knowing what that actual numerical value is, I can see that it's a true statement. All right, let's take a look here. In this case, I don't know how to solve it just as is. I can't type it in my calculator as is. So I'm going to need to convert to exponential. So if I convert to exponential, my base becomes my base, my answer becomes my exponent, and what's remaining becomes my answer. So remember that from yesterday's lesson. So we actually did some of these yesterday. So in this case, we just need our 5 to the 3rd to get our 125. Now, I can check again in my calculator if I'm unsure. If I type in log of 125, divide by log of 5, I will end up with 3, so I know I'm right. Take a look at another one. If I change this around and I convert, I would have my base become my base, my answer become my exponent, what's remaining becomes my answer. So if I take a look at that, what to the 5th power would get me to 32? So in this case, you could use your chart or you could use your calculator to solve, but we end up with x equals 2. Let's take a look at another one. In this case, I have an expression. So my first thought is I have no idea what my x value should be. So I'm going to convert to see if that helps me out. So my base becomes my base, my answer becomes my exponent, and what's remaining becomes my answer. So similar to our lessons before, I can do my basic exponents. And in this case, all I have to do is add that 4 over. So pretty straightforward. Again, I can double check my answer. If I was to plug in that 12, 12 minus 4 will be 8. And if I wanted to use my calculator, log of 8 over log of 2 would get me to that value of 3. Let's take a look at another one. If there is something that's sort of lingering, it's out of place, it can't be paired up with the log itself, then kick it to the other side. Make it so it looks like all of the other problems that we've been working with. So in this case, we end up with -3. Negatives are okay. Let's do a little more work. I'm going to convert because I'm not sure how to find x otherwise. So the base is the base, the answer is the exponent, what's remaining is my answer. So 10 to the -3rd, you got to remember those those exponent rules that deal with fractions. So a negative is going to kick that 10 to the bottom, make the exponent positive. Then I need to take care of that exponent, use 10 to the 3rd, and get 1 over 1,000. Pretty easy to check this answer actually. Since it's a base 10, if you were to plug this in, you could plug it in just like this. 7 plus log of 1 divided by 1,000, and you should end up with 4. Let's take a look at one more. In this case, my unknown is the answer. So converting doesn't help, but if you forget, if I was to convert this, it would be 2 to the x equals 5. Well, no exponent that I know of off the top of my head gets me to 5. So this is not helpful. So in this case, I'm just going to solve using my calculator as I see this. So if I type in my calculator log of 5 divided by log of 2, I'm going to end up with a decimal. So plug that in, and I would like you to round to the nearest thousandth. So thousandth would mean how many decimals? 3. So I'm going to say x is approximately 2.32, and I would round up that 3rd decimal since the 4th one is a 9. So all of these examples can be combined in one way or another. The end goal, no matter what, is to solve for x. X can be a nice clean number. It can be a crazy decimal. You might deal with some fractions, so don't let your idea of this should look pretty in the end work out. You can end up with all kinds of numbers when solving for x and using logs. Make sure you check Google Classroom to see what else you need to accomplish with this lesson, and let me know if you have any questions. We'll see you next time.